Hello, this is Eduardo Suarez. In this video, I'm going to show you how to program spiral motion in RoboGuide using KAREL programming. We're going to start by creating a new work cell. In this case, I have the work cell already created, and I added the KAREL option package R632. If you want to see what option package is already created in the work cell, you can go to the C controller. You can right-click, just go to Robot Controller Properties, and you're going to see here all the options that includes the KAREL R632. If you are in the real robot, you can go to the Teach Pendant. So we're going to open the Teach Pendant. And we're going to select Menu. We're going to go to Next. And we're going to go to Status. And we're going to select Version ID. If you don't see this screen, you just can select Type and Version ID. Then we go to Next, and we go to Order FI, and you can see here again all the option packages. You have another option, you have another way to do that. If you don't wanna go through the menu, you can select Status, and it's gonna bring you back to the same page. I'm gonna do a few things before we start writing our first program. We're gonna add an from tooling. We're gonna go to group 1 on the work cell. In the cell browser, we're gonna go to Tool. We're gonna select User Tool 1. We're gonna right-click. We're gonna select Add Link, and we're gonna select the CAD library. The CAD library is gonna show up. Then we're gonna go to the from tooling, and we're gonna select Pointer, and OK. So from this screen, on this window, we're gonna close it, and we're gonna select that again, and we're gonna go to from tooling properties. We're gonna go to the user tool, and I'm gonna manually change that value and apply. And you can see now, if we open up again the Teach Pendant, we can go to Menu, we can go to Setup, we can go to Frames, and we have already the Tool Frame 1 with the changes I made. We're going to make another change. We're going to select Data. We're going to select the position registers, and we're going to change this one to, we're going to change the description. We're going to call it Home, and I'm going to press Shift and record. And what I'm doing is just recording the robot position. That's going to be my home. And then we're going to select the next position register. We're going to go to Position, and I'm going to set all the values to 0. Done. Next, we're going to change the coordinates to world. Now we're going to start creating our first teach-pendant program. We're going to go to select. We're going to use create, and we're going to name our first program. We're going to call it move to position. We're going to edit, and here we're just going to add a remark. We're going to add a point, and we're going to change this position to a position register 1. We're going to add another remark. And we're going to add another point. In this case, we can use this one in here, and we're going to change this one to position register 1. We're going to change this one to 2000. We're going to change this one to 5, and we're going to select choice, and then we're going to put an offset with a position register, and we're going to select position register 2. And this is all that we need to do for our teach pendant program. It's only going to be 2 move instructions. We can close the teach pendant for now, and we are ready to start creating our first KAREL program. We're going to select File from the cell browser. We're going to select New, and we're going to select KAREL Source. From here, we're going to save it and rename it as set position register 2. And this is the first program we want to create. This is not the final version that we need for the spiral yet, but this is going to give us an idea how the movement is going to be created and how we're going to get to making the spiral motion. What we have in here in the data declaration section, we're going to start with a variable that's position type. This type is position data. That's the kind of position that we need for the reading and writing the position register. Then we're going to have an increment that's going to be an integer. The increment is going to give us the position in millimeters that we're going to be incrementing the position register 2. Then we're going to have a counter. Counter is going to be part of the for loop, and it's going to be just incrementing or multiplying the increment that we're going to offset the position register 2. And then we have a couple of another integers, that is status, that's coming from when we read the position register, and the program index that is used as an input and output for calling the program. And any of these 2 variables need to be initialized. On inside the program, what we have in here, we're going to set up the increment to 100 millimeters, and we're going to put the counter to 1. First thing we're going to do, we're going to read the position register 2 with this KAREL statement. Here, number 2 is the position register that we are reading, and status is an output from the instruction that if the value is 0 means that it was successful. And we're going to get the position register on the variable position that we had defined before. Then what we're going to do for the position register index X, we're going to set it up to 0. So we are initializing the X-axis, and then we're going to write it back the position register 2 with this position offset that we have already defined. We're going to call the program move to position. There are 2 instructions for calling the program. One is called program and the other one is called program line. The first one in here is going to start calling the program from the first line. So what it's going to do, we're going to execute go to home and then go to position register 1 with the offset for position register 2. And then we're going to have a for loop with a counter that goes from 1 to 5. That what it's going to do is going to increment the position offset on the X-axis for the position register 2, but the increment that we have already predefined is going to be 100 millimeters, and a multiplier that is going to be coming from the for loop. Then we're going to set again the position register 2 with this new offset, and this time we're going to call the move to position with this another instruction that is going to specify that we're going to start calling the program from line number 4. So we're going to try this one. We're going to save it, and we're going to build the program. The translation was successful, and we're going to do one more thing. We're going to close this one for now. We're going to go to programs in here. We're going to right click, and we are going to add a simulation program. In our simulation program, we're going to create the first instruction, and we're going to make a call. But you're going to notice something in here. We just try to make this a call instruction, and we go to the selection menu in here. You're not going to find any program for the KAREL. So we're going to go back in here, and we're going to delete this instruction. Instead of that, we're going to go back in here again, and we're going to call the remark. And this time, we're going to use the remark with a question mark. These 2 special characters, remark and question mark, what it's going to allow you as is enter an instruction similar to the teach pendant. So we're going to do a call to our KAREL program that's going to be set position register 2. And now we can try to run this program and see what happens. we're going to open the teach pendant. We're going to go to position register 2, and we're going to go to position, and to be more clear, you're going to see here what happened when we run the program. You're going to notice that it's going to set the x-axis to 0, and then it's going to start incrementing by 100 millimeters to 200, 300, 400, and finally to 500 millimeters, following the for loop. We're going to run this one again. Go back to 0 and keeps incremented by 100 millimeter 5 times. What we have done so far is a very simple linear motion, and we can go back again to analyze how this one happened. So we're going to select here our teach pendant program, move to position. You see here that first we're going to go to home with the position register 1, and then we're going to move linear to position register 1 plus the offset that we are setting up in position register 2. And this offset is just coming from our KAREL program. We're going to open the KAREL program one more time. We're going to put it side by side. And you can see here that what we're doing is just setting the position register 2 on the x-axis to 0. We don't need to set up any other axis because they are already 0. We are not going to modify them. And then we're going to call we're going to set, write it back the offset to position register 2. So what we're doing is overriding the axis with a 0. Then we're calling the move to position program. That means that it's going to go to home first, and then it's going to go to home plus the offset that is 0, that basically is not moving. This is going to go back in here again to our KAREL program. And next time, what are we going to do? It's going to enter in the for loop, and we're going to have already the increment that was set up to 100 millimeters. We have the counter coming from the for loop that's going to start with 1. We are going to set up this time the position offset on the x-axis to 100 millimeters. We're writing this one back, so this time our position register 2 on the x is going to be 100. We are calling again the teach pendant program, but this time we're going to start executing from line number 4 instead of line number 1. So we're going to start from our last position, and this time we're going to move with the offset for position register 2. That's going to be 100 millimeters. And that just we just keep moving again with the for loop. From here, we have already set up the initial conditions that we need for creating our spiral motion. So we're going to close these programs in here, and we're going to start again with our next step. The next steps is to understand how the spiral is created. I did a search on internet and I found this article from Wikipedia that is the Archimedean spiral, also known as the arithmetic spiral. The way that this one works, you need to look at this coordinate system. We have two Cartesian coordinate systems. One is x, y, and the other one in blue, XY, that is on the same origin. You can think for a moment that these two axes or these two Cartesian coordinates are aligned. So this X in blue is aligned with the X in green. The Y in blue is aligned with the Y in green. And we have a point that is traveling at constant speed along the x-axis. After that, we start rotating the second coordinate system at constant angular speed. So in that way, this point is moving along the x-axis at constant speed, and at the same time is traveling at constant angular speed. The formula is what you see here in all this, and at the end you're going to have this pattern created. What is important to notice here is the speed. If you know the distance that you want to travel in 368 degrees, let's say in one full rotation, if you know that distance, you can calculate the speed by dividing the distance by 360 degrees. If you want that, you want to get that in degrees, or 2 pi if you want to get that in radians. So to understand that, what I did in here, I created that formula in Excel. So we have in column A, this is going to be the distance that we want to travel in a full rotation. It's going to be 200 millimeters. On the column B, I started to increase the angle. I have the angle in degrees, and I'm stepping by 5 degrees at a time. Then we have the radius. The radius is going to start incrementing linearly. It's going to be the angle multiplied by the full distance and divided by 360 degrees. And then we need to calculate the x and the y coordinates. That's going to be the radius multiplied by the cosinus of the angle. And on the y-axis is going to be the radius multiplied by the sinus of the angle. And then we can plot this, and you can see the result. In this case, I went over 2 full rotations, so up to here we're going to have 360 degrees, and the next is going to be up to 720 degrees. You don't know how this is created, well, we can delete this. We can select the x and the y. That is going to be our data. Then we can go to Insert, and we're going to select Charts and Scatter Chart. And here we have this pattern. And this is what we're going to do on our KAREL program. Going back to RoboGuide, we're going to open our KAREL program, and we're going to create a new version. We're going to call it Set Position Referring to Version 2. And you can see here that I have a few more variables created. First thing we're going to do, we're going to read the position register 2. And in this case, we need to initialize the x and the y axis because they are going to be modified by our program. Then we're going to set the position register 2. We're going to do exactly the same we did before. We're going to call the program move to position. Then we're going to initialize the radius. We're going to initialize the number of turns. That's going to be 2 full complete turns. and the distance that we want to travel in full rotation is going to be 200 millimeters. And we want to create a for loop again, but this time we're going to increase the angle from 1 to 360 degrees. Then we are going to calculate the radius. The radius is going to be the full distance that we want to travel divided by 360 degrees and multiplied by the angle. Notice that in this case, instead of using just the angle from the for loop, I'm multiplying by the number of turns. So instead of going just by 1 degree at a time, it's going to be 2 degrees at a time. And you can notice in here that the radius is calculated the same way that we did in the radius on the Excel file. Then we're going to have the x component of the radius. That's going to be the radius multiplied by cosine of the angle. In this case, just remember again, it's going to be the angle multiplied by 2. And then we're going to have the y component that is going to be the radius by the sine and the angle again. The same way that we did with the x component and the y component. The only difference here is that on the Excel, it asks for the radius or the angle in radian, but in this case, in the KAREL program, we can put the angle in just in degrees. Then we're gonna put the offset on the X and the offset on the Y for the position register. We're gonna set again the position register 2, and we're gonna call the program move to position, in this case, by starting in position 4. We're going to save it. We're going to translate. Translation was successful. And this time, we can run the program. We're going to open our simulation program. We're going to change the name to version 2. And what we're going to do here, we're going to open the RAM panel, and what we want to get in here is going to be the options for collect the TCP trace and show during a run. Just I want to let you know that this is going to be a very slow motion. So what I'm going to do, I'm going to speed up the video to show you this one in a faster way with the final result. We're going to run it one more time, and this time I'm going to show you the position from a different angle, and also I want to show you the position register 2, how this is changing. And let's go again. I'm going to show you now how to do a backup and a restore of the programs. We're going to open the teach pendant. We're going to go to menu, We're going to go to File and select File again. And in here we have already UT1 selected, but if we don't have that, we go to Utilities, we go to Set Device, we go to Next, and we select the USB drive. Now we're going to do a backup of the project files on the USB drive. We're going to select Backup, and we're going to select all of above, and we're going to say yes. And here is doing the backups. When it's finished, we can close the Teach Pendant. We can go to Tools, and we can select the project folder inside the My Work cell. We're going to select Robot 1, and we're going to select the folder for UT1. And here you're going to have all the files. The files that we're interested in is going to be Move to Position, that is the TP program, and the Set Position Register 2 version 2 PC, that's going to be the P-code file, and the variables. So we're going to select these three files. We're going to copy that. And now let's say that we want to restore these files in a real controller. For that purposes, we're going to select another work cell. We're going to select Tools. We're going to go back again to the folder, Robot 1, UT1, and we're going to copy it in here, simulating that we have already the USB connected on the terminal on the Teach Pendant. We're going to open the Teach Pendant. We're going to go again to Menu, Files, and File. We have to make sure that we have again UT1 selected. And this time, instead of doing a backup, we're going to do a load. We're going to say yes. And the files are already loaded. If you want to see that, we're going to go to Select. And we have in here, Move to Position, if we have selected the TP programs. And if you want to see the KAREL programs, we just select KAREL programs, and you're going to find the Set Position Register 2 version 2 loaded. Before I conclude with the presentation of this video, I want to give you a few assignments. First assignment, get the KAREL reference manual and read about all the KAREL instructions that we have used in this program, especially the position data types that we're using. You're going to find that there are different types of position data available. Second assignment, you can modify the program and add a linear motion on the z-axis. Assignment number 3, you can try to replicate this KAREL program using a Teach Pendant program. I believe that you're going to need the math function option package J593 that's going to provide additional instruction to the Teach Pendant editor, allowing advanced math functions. Assignment number 4, if you go back to the arithmetic spiral article on Wikipedia, you're going to find a link to the logarithmic spiral. You can try to do this motion too. And finally, as usual, please leave your comments below.